Okay, so this is notes for Thursday, March 21st, and I finally did give out the review sheet and the homework sheet, and just somebody really quick, if you happen to have the review sheet, never mind, I have one here. Um, yes, that is the way, because I had kind of two thoughts, but that is the way that part one and part two will be broken down. So I did give you the breakdown of those two parts. I am having a help session tomorrow morning from 7:30 to 8:15 if you'd like to come to that, and tonight after school if you'd like to do it then. And so you have the review sheet, the homework sheet, and then really we have to finish these roots of complex numbers. So I'm just going to remind us of some, like, just previous work. So if we have x squared equals 64, then we have x equals 8 or negative 8. So that's like the basic idea that's happening here. And roots of complex numbers, we know that we can have I now and things like that. But what we're maybe not knowing from our work so far is, suppose I have x to the 6 equals 1. And we know that the fundamental theorem of algebra, from that a polynomial equation of degree n has n solutions in the complex number system. So that means x to the 6 equals 1 actually has 6 solutions. So that's maybe a little unusual seeming to us as we look at it. And then here, some are maybe repeated values, or or let's kind of think about what's happening here as we go. So x to the 6 minus 1 can be x to the third minus 1 times x to the third plus 1. And then there is a formula for a cube minus a cube and a cube plus a cube, and these are those formulas. So you know that positive 1 and negative 1 are going to be roots, because that should make sense. 1 times 1 times 1 times 1 times 1 times 1 times 1 is 1, and so that 1 to the 6th and negative 1 to the 6th will also be. And then you could use the quadratic formula there. These are not factorable, but the quadratic formula would give you those complex roots, right? And so actually, you probably didn't think of this before, but the 6th roots of 1 are actually these 6 values. So if we have x to the 6 equals 1, or x to the 6th minus 1 equals 0. So x to the 6 equals 1. Every one of these 6 things, when we raise it to the 6th power, is equal to 1. And so that's digging deeper into kind of the mathematics that we go. And the way that we're going to do that, if you remember, we did the trigonometric form of a complex number, and then we raised it to powers. Well, just think about, now we're going to find the roots of those. Just like in mathematics, a long time ago, you first learned how to square numbers, and then you learned how to square root numbers. And so this is kind of that opposite kind of thing as we go. So the definition of the nth root of a complex number, if the complex number u is a plus bi, so that's what we're talking about in this section, then the nth root of the complex number z, when z equals u to the n, or is z, when z equals u to the n. So a plus bi to the n. And we know that we've been able to change that into trigonometric form. And so we'll kind of go through the process here. And that gives us the definition. But we're going to have a way of kind of figuring this out as we go. And so We'll just kind of go through these slides a little bit on the quick side, so I'll just kind of show them to you. So if u is the nth root of z, where it's in now this trigonometric form, we can use de Moivre's theorem, and we've talked about that. That means that s to the n cosine n beta plus I sine n beta is gonna be, you know, matching that trigonometric form as we go. And then if we take the absolute value of each side, then substitute back in the previous equation, what happens is, since sine and cosine both have a period of 2 pi, these work if they differ by multiples of 2 pi. So then we find that there's an integer. Let me see. There we go. And so this is what I want you to have, is the equation. So how about that? We just went, you know, completely boom right through that. So yes, there are a lot of equations. So if we have to find the nth root of a complex number, and I rewrote it over here. It's not quite as intimidating as maybe it seems right here. But so if our complex number z is r parentheses cosine theta plus I sine theta, it has exactly n distinct nth roots given by z sub k, where k is 0, 1, 2, 3, 4. So we kind of find a bunch of these as we go, because we know if we're taking the sixth root, like that first one, then we would have k sub 0, 1, 2, 3, 4, 5. Do you agree with that? Because this k starts at 0 and then, goes to 5 as we look at that. And so it's r to the 1 over n. So think about that as like when we were finding the sixth root a minute ago. So to the 1, r to the 1/6. And then cosine theta plus 2 pi k divided by n. And so, you know, well, the only real difference between powers and roots here is that we have to put this k in multiple times. And then, you know, think about this. When we were taking a power, we took r to the power. Now we're taking r to the root, correct? So that modulus is going to the root. So that's not super earth-shattering. And then the angle, when we were taking it to a power, we multiplied by n. Well, now we're dividing by n, but we do have that little extra trickiness that we have to kind of think about these revolutions and kind of spins as we go through that. So in my mind, the formula isn't super hard because we take r just to the root, just like we did to the power, and then we divide. The only difference is we have this plus 2 pi k. The real thing that kind of is maybe a lot of work is that it is very repetitive in nature. So remember, if we're finding the 6 roots, then there are 6 answers. Do you agree with that? So essentially, if there's 6 roots, we have to do this 6 times. But you know what? If you have to do it 6 times, then you should figure it out by, you know, number 6. You should be able to. You're gonna have to be able to do that. Yeah. So you ready? Okay. Well, good. Awesome. And do you have this written down? Okay. All right. So that's going to be a good thing. And this just goes through the kind of finding those angles as we go, and I think you'll see that happening kind of as we um, as we go through this, and I think you'll find that this happens. Now we're gonna do a problem that we know the answer to. So we're gonna find all of the sixth roots of 1. So if you were super on target, you maybe wrote all 6 of those down from before, and if not, that's okay because we're gonna figure them out. And I think that'll help you kind of figure it as we go. So maybe I have a slide. Okay, yeah, I don't like that one anymore. Okay, so there are 2 steps. First, this is not in trigonometric form. So step 1 is to write things in trigonometric form. And then step 2 is going to be to find the root. So step 1 is to write the number 1 in trigonometric form. So kind of think about that. A plus bi, the plain old number 1 is 1 plus 0i. Do you agree with that? So we'll just go 1 plus 0i. So that is it that way. Then I'll kind of think about where that point is on the complex plane. So it's at 1, 0. So maybe I'll put my little dot right there. And so that's 1, 0. And we know that's cosine comma sine. What's the radius? R. 1. And so if we turn this into a complex number, z, that is 1 times cosine, what's our angle? 0 plus I sine 0. Do we agree with that? So, and so that is the complex version of kind of that number 1. And so it started out real. So step 1 is just done. Then for step 2, we're going to find the root. And so we're going to do this equation 6 times, and if you write it down and kind of pay attention, it's a pattern. It's just a repeated pattern as we go. So we know that z sub k equals, and I'm going to write it like this, the nth root of r, because that's r to the 1 over n, just to kind of think about that. And that's not going to be a huge issue here because r is 1. Times the cosine of theta plus 2 pi k over, n, plus I sine of theta plus 2 pi k over n. Oops. I think I can get that in there. So then where k equals, and since it's the 6th roots, k always starts at 0. And we've had situations where things, if we have 6 of them, we start at 0 and go to 5, right? We've done that in other instances before. So k is going to equal 0, 1, 2, 3, 4, and 5. So we do this 5 times. And so I just want you to allow yourselves to kind of see how this works, and that it's not as intimidating as possibly you think right at this moment. And we'll do another one after this, and then that'll be good to go. So the nice thing about this is, what is r? It's 1. So any root we take of 1 is just going to be 1. So I'm just going to do this z sub k equals, I'm not going to put in k yet, but I'm going to put in the things I know. So it's going to be the 6th root of 1. And whatever that is, it'll be the same for the whole thing. Cosine, since our theta is 0, so do you want me to write the 0 plus 2k? Okay, 0 plus 2 pi k over, what's n? 6 plus I sine 0 plus 2 pi k over 6. And so you'll see what happens as k is equal to 0, 1, 2, 3, 4, 5, and 6. It's just going to work us right around the unit circle as we go. So maybe I'll just clean this up a little bit before I start doing my 6 versions of that. Well, once you figure this out, it's the 6th root of 1, so it's just 1, right? And it's going to be the whatever root of some number, and it's always going to be the same, correct? And so in this case, that 1 is not going to change. Well, now look at this. Since that's 0, it's going to be 2 pi k over 6. And can you reduce the 2 over 6, right? Yes? Yeah, so it's going to be pi over 3, times k, so to speak, or pi k over 3. So cosine of pi k over 3 plus I sine of pi k over 3. So what's our reference angle going to be, do you suppose? Look at it again. Pi over 3. Our reference angle is going to be related to pi over 3. Does that make sense? And so that's how we're going to, kind of progress as we go. And since this is a 1, I can ignore that now, but I know that if it weren't 1, I would have to, just figure that out. So I'm going to put pi k over 3 plus I sine pi k over 3. So essentially, I'm just going to go through this, and I'm going to do this exact equation how many times? 6 times. 6 times, I'm going to do this equation, but open your mind so that you can kind of think about this, because if you're paying close attention and you're seeing what's happening in this pattern, it should make sense as we go through this. So when k is 0, what am I going to get for these angles? 0, right? So I need, and maybe I'm maybe going to slide this way over here just so that I can kind of, so I need z sub 0, z sub 1, z2, z3, z4, z5. I wanted to get them all together here, so maybe, there we go. Oh. And then z6. So I wanted to kind of get them all in this same spot. So when I put in 0, it's going to be cosine 0 plus I sine 0. When I put in 1, it's going to be cosine pi over 3 plus I sine pi over 3. When I put in 2, it's going to be cosine 2 pi over 3 plus I sine 2 pi over 3. When I put in 3, it's going to be cosine, well, what's 3 pi over 3? Pi. Cosine pi plus I sine pi. Ooh. And when I put in 4, it's going to be cosine 4 pi over 3 plus I sine 4 pi over 3. When I put in 5, and I'll just slide this down a bit for myself. When I put in 5, it'll be cosine 5 pi over 3 plus I sine 5 pi over 3. And then the last one is cosine of what? 2 pi, right? Because it'll be 6 pi over 3. I do. No. Oh, yes, I put 6. I put this one on here. That is right. Because I'm not actually going to do this one. Because what does it do? it equals the same. So if I kept going kind of forever, do you agree they would just match those, right? Thank you for that catch of that. So those 5, and do you notice that just wound you right around a unit circle, correct? And the reference angle is pi over 3 for all of these. Do you agree with that? So we know what the sine and cosine of pi over 3 is, so we just kind of have to figure out what all those reference angles are as we go. So I'll kind of put my chart over here, sine, cosine. Pi over 3 is right there, I think. And what's the sine of pi over 3? Sine of pi over 3? Oh, yeah, it is. I'm sorry. Yeah, I was just saying no, but I should have been saying yes. Square root of 3 over 2. Cosine is 1/2, correct? And we do have 0 in there, so what's the sine of 0? 0. Cosine of 0 is 1. So let's just kind of put these in and think about our all students take calculus and see what happens. So cosine of 0 is 1 plus I times sine of 0 is 0. So this is 1, which we knew was a root anyway. And then cosine of pi over 3 is 1/2. 1/2 plus I times sine of pi over 3, square root of 3 over 2. You know what? I think, is it okay if I just write it with the I in behind? Square root of 3 over 2I. Um, 2 pi over 3, so I'll kind of write my little picture across from this. 2 pi over 3 is now all students take calculus is over here. Do you agree? So sine is positive, but cosine is negative, correct? So this will be negative. What's the cosine of pi over 3? 1/2. And then the sine is going to be positive plus the square root of 3 over 2I. Are you seeing how really once you know what the reference angle is, it's just using this pattern as we go around that and do those revolutions. So then the next one, we're at pi, which would be the point -1, 0. And so that's cosine and sine. So we'd have -1 plus I times 0. And so there's our -1, right? The next one, 4 pi over 3. Think about where that is. That's down here. All students take calculus. What's true about sine and cosine in that quadrant? Both negative. And so we know what cosine and sine are. So it's -1/2 minus square root of 3 over 2I. And then the last one, for the cosine of 5 pi over 3, we're in this quadrant. All students take calculus. Cosine is going to be positive, and sine is going to be negative. And so it'll be, cosine is positive, 1/2 minus the square root of 3 over 2I. And then think about those answers that we know are the square root of, or the 6th root of 1. +1 and -1 are kind of a pair as we go. And then, like, you know, when we use the quadratic formula, we would get these two as a pair, 1/2 plus or minus the square root of 3 over 2I. And then the other pair is -1/2 plus or minus the square root of 3 over 2I. Pardon? Yeah, really, I mean, I feel like you just didn't give it a chance right at the beginning. And it's really just, pardon? I'm sorry. I'm apologizing to the students now because somebody gave me an answer and I said they were wrong and I was wrong. Okay, so now we'll do one where it's the cube roots and it's not just 1 and r isn't going to be 1. So this is kind of our second example here as we go through this. So this one is going to be a little bit more challenging, but it's all this patterning that we are kind of do as we go through it. So we want the 3 cube roots of z equals -2 plus 2i. So our step 1 is put it in trig form. Put in trig form. And that's something you have to do in this chapter anyway, correct? Is put something in trigonometric form. And I guarantee that is on the test, putting things in trigonometric form. So our z equals -2 plus 2i. And so if we get r, how do we get r? Yep, square root of a squared plus b squared, so square root of -2 squared plus 2 squared. 4 plus 4, it's the square root of 8. R is the square root of 8. Now, do I want to, I don't know that I want to put that as 2 the square root of 2. Do you know what I mean? Which is what we've often done. I might write it as 2 to a fractional power and kind of think about the fact that I'm going to take a fractional power of that as we go. But right this second, I'm just going to leave it as the square root of 8. And then my point is at -2, 2, so I'm up here somewhere on that complex plane. And what's my reference angle? 45. And so, you know, it's when the tangent of theta is 2 over 2, so the tangent of theta is 1. So my reference angle is 45 or pi over 4, correct? If I put it in radians. Oh, but you know what? You said 45. I kind of looked here. Do you want to do it as degrees so that we've done a degree one? Because it could be degrees or radians. You tell me. Okay, degrees. So we'll do this one. The reference angle is 45 degrees. And if that's 45 degrees, what is theta? Those are the reference theta. What's 180 minus 45? 180 minus 45. So theta is 35 degrees, or 135, sorry. Yeah, I'm 135 degrees. So this z in trigonometric form is z equals the square root of 8, parentheses, cosine 135 degrees, plus I sine 135 degrees. And we just will have to, you know, instead of using 2 pi now, we're using 360, correct? So that'll be a little difference in our minds. And now I'm going to move to step 2. So step 2 is to kind of find this root. And so I'm going to just start writing my z sub k is, and I'll just write it, you know, as is right now. So it's this 1/8 to the what power? Because I'm taking the cube root. To the 1/3. Does that make sense? Or the cube root. So to the 1/3, and I'm going to clean that up. But once I clean it up, then it'll be the same no matter what. Cosine of 135 plus, what do you think? I'm in degrees now. 360k divided by n. Oh, n is what? 3. Plus I sine 135 plus 360k divided by 3. And so now let's kind of just clean this up a little bit. Let's kind of think about this square root of 8 a minute. Do you agree that this is the square root of 2 to the third, right? 2 times 2 is 4 times 2 is 8. So this is 2 to the 3 halves is the square root of 8. Do you agree? So then over here, this is 2 to the 3 halves raised to the 1/3 power. So what is that? Two to the what power though? The 3's cancel, but what will that be? 2 to the 1/2. 2 to the 1/2, so it's going to be the square root of 2, back to the square root of 2. So when I do this this time, 3 times, right, is all I have to do. Do you agree? 3 times, because that'll give me my 3 answers. I'm going to use the square root of 2, cosine 135 plus 360 k over 3. I'll just leave it that way for now. I sine 135 plus 360 k over 3. And what's k going to equal? K equals 0, 1, 2, right? So k equals 0, 1, and 2. So z sub 0 is going to be the square root of 2 times cosine. What is 135 plus 360 times 0 divided by 3? So it's going to be 135 divided by 3, right? What is that? It is 45. Yeah. Do you agree? And do you remember what our reference angle was a few minutes ago? It was 45. Yeah. So there's a relationship there. So cosine 45 degrees plus I sine 45 degrees. So we're just going to get, I'm going to leave myself a little room right there just because I feel like I don't have enough room over there. So z sub 1 is the square root of 2 times. Now, somebody help me with that. What's 135 plus 360 and then divide by 3? 165. Cosine 165 degrees plus I sine 165 degrees. And then z2 will be the square root of 2 times, what is 135 or 135 plus 360 times 2 divided by 3. So 720 you're adding to 135 and then dividing by 3. 285 cosine 285 degrees plus I sine 285 degrees. And actually, you know, I do sometimes do that next one, because if I put in 3 there, it should get me what as my angle? Well, try it and see if that makes sense to you. Well, put it in there and see. And then that'll kind of give you that idea. Now, what's the reference angle in all these situations? What's the reference angle? It's 45 degrees, maybe, or, you know, maybe not. 165, no, it is not, right? Is it? No. 165, it's going to be like 15 as a reference angle. So when that happens, if it's on our table as a reference angle, we're going to do it as the table. But if it's not on the table, we have a calculator in front of us, we're going to get it as a decimal approximation. Okay, so I do need a little calculator support. But this first one we can do, what is the cosine and sine of 45? They're the same, right? Square root of 3 over 2. So I'm going to take the square root of 2 times the square root of 3 over 2. Square root of 2 over 2. Yeah. Wow. Yeah. Times the square root of 2 over 2 plus the square root of 2 over 2i. So what is that going to be when you distribute that square root of 2? So 2 over 2 or 1, do you agree? Because square root of 4 over 2, which is 2 over 2, which is 1, plus, and 1i. 1 plus I for that first one. So that's just whole number things, so that's easy. These are going to be easy because we just have to use a calculator for them. It looks like I rounded to 4 decimal places. So what's the square root of 2 times cosine of 165? In degrees. Make sure your calculator is in degrees. Yes. Plus something I. So the sine of 165. And think about the fact that, 165 is over there somewhere. So all students, so sine should be positive. What did you get? I. And same thing down here, square root of 2 times cosine of 285. So this is 270 there, 285 is all here. All students take calculus. Cosine should be positive, sine should be negative. What do you have? 0.3660 plus, I was going to write, but it'll be minus. Minus what? So isn't that interesting? Maybe. So that is the end of this lesson, and so here's what's happening now. And you have review time. There's maybe 9 minutes left of this class period. Tomorrow is just your complete review day. Tomorrow morning is the AM session where I go over problems just like these sets of problems, and then the exam part 1 will be on Monday. The exam part 2 and the homework will be due on Tuesday. You can check homeworks, any homeworks tomorrow in class as well.